Hi, this is Jeff Coronado at JCSC, and this is a session in Bridging the Gap. In this particular session, well, before I jump into that, let's cover a little bit just Bridging the Gap. For those of you who are not familiar with Bridging the Gap, I invite you to take a look at the introduction in our YouTube channel to get a little bit of a sense of the background, what we hope to achieve with Bridging the Gap sessions, who kind of they are intended for. So hopefully you will find that helpful. This current session is in the sequence of sessions of W17. It's one of the W17 tutorials. In particular, what we're going to be covering here is an outrigger, and it's the lateral torsional buckling of the outrigger. So it applies to the outrigger. It also applies in general to a beam that has an overhang, a simply supported beam with an overhang. So that's the nature of the lateral torsional buckling that we're going to be covering here. Okay, with that in mind, let's jump into the particular detail that we want to take a look at. And so here we have, so again, this is W17. It's an exterior non-bearing wall roof condition. You can see here how the rafters are going in and out of the page. Here's your stud wall, and here is the outrigger. So the outrigger is intended to cantilever beyond the edge of the wall and support the roof in that overhang. All right, so what we've got is basically a simply supported beam with an overhang. So if we were to do, you know what, I'll go off here. Okay, so what I've drawn for you here is basically again, it's a simply supported beam. This is how we would model it, right? So it would be modeled as a simple support here at the wall, a simple support at the first rafter, and then it overhangs beyond the wall. Okay, so you're going to evaluate this beam on your software package, whatever software you use. Some of that isn't going to be covered here in this session. Again, primarily what we want to focus on is the lateral torsional buckling entry. So, but let me take you to the software output. Okay, let me clear the screen. Again, what we're focusing on is the entry for the bracing of the compression edge to prevent lateral torsional buckling. All right, so you can see here how we've got our beam modeled, simple support, and then the beam overhangs beyond the simple support, which is what we've now covered. And so now we've got to cover the lateral torsional buckling. So intuitively, what you either should know or what you will get to a point where you are comfortable in this is that now I don't want to get too much into lateral torsional buckling because I know that we have other Bridging the Gap tutorials sessions that cover in a more general approach what lateral torsional buckling is. Hopefully, if that's an area that you are interested in knowing more about, you can search for those on our channel to get a background, a better, more broad background on the treatment of lateral torsional buckling. But I'm assuming you've now covered that. So we're trying to cover lateral torsional buckling in this particular type of situation. So you would know that this overhang is going to deflect down. That means that your bottom fibers here for this beam are the ones that are in compression. Since there is no sheathing along this compression edge, this edge is unbraced. So for sure, you know that the overhang is unbraced, okay? So there is no bracing in this segment. Then the question becomes, what about the back span? What about the span that's between the simple supports? How much of that is unbraced, or is it all unbraced, or is none of it unbraced? Intuitively, you will start to develop a sense for that. It depends a little bit on the span, on this span compared to this span, in terms of how much of this is going to be unbraced. But certainly the simple approach is to simply look at it. And the way you can look at it in your output is by scrolling down and looking at your moment diagram. All right, so this is schematically the moment diagram. And what the moment diagram is telling you is that the entire length of the element has the bottom fibers in compression. So the support was right around here. Oops, let me redo that. Let me just draw a straight line here. So the support was right, probably in line right here. All right, so the left side of this moment diagram is the contribution from the or is reflection of the moment diagram to the left of the wall, and this what I'll highlight maybe in yellow is the moment diagram of the outrigger between the supports. But either way, in both cases, what you are seeing is that the moment causes compression on the bottom fibers, both on the left side as on the right side. This moment diagram never goes positive. Okay, that's the important thing here. The moment diagram is always below the zero line. Right? If this is our zero line here, the moment diagram never goes above. So what that tells us, the moment diagram never goes above, right? Never does this. What that tells us is that the compression is always on the bottom side of the outrigger. So if we go back here, what that tells us is that both spans, then this span as well as this span, both spans of the outrigger are unbraced. So that's how you would have to model this outrigger. Okay, so hopefully you find that helpful in understanding how to determine what the unbraced length is for an outrigger. So yes, that concludes this session of bridging the gap for the outrigger and in specifically determining the lateral torsional buckling. Again, for other topics that would be related to that detail that we were looking at, W17, you can search for those in the library. I'm sorry, in the channel, in the JCSE LLC channel. Please feel free to leave us any comments, suggestions, or questions that you might have. And if you enjoyed this session, please give us a thumbs up, as well as subscribing to our channel so that you can receive automatic updates on when new posts of this nature are put up. Okay, real good. Thank you.